tried to add on security mechanisms, but as always, it's hard to get things right. And so even when they've added things on, they have ended up being sort of catastrophically bad. And the third mistake that people made is a lot of people thought that the internet protocols like TCP/IP were secure and they trusted them for security when they were not actually designed with security in mind. And so people sort of made bad assumptions about how secure the internet was early on and trusted it when they shouldn't have, and sort of built systems that were based upon that trust. So we're going to talk about the internet protocol attacks, some man-in-the-middle attacks, something about address resolution protocol spoofing, some 802.11 wireless networking attacks today. Okay, so here's sort of a diagram of our internet, and the first thing we have to know always is what is our threat model? Who are we worried about attacking us in this model? So we worry about malicious hosts. You know, these are machines that are on the network that can send arbitrary packets or receive arbitrary packets, but they can't manipulate the network infrastructure. So this is all of us. We are all these end hosts. We can, you know, send and receive arbitrary malicious packets on the internet. Second, we have subverted routers. So it might be that you can compromise a router, you know, like a wireless router in somebody's home or the router at an enterprise to sort of see all the traffic going by or to inject packets. And then finally, we worry about sort of the whole backbone network potentially being malicious. So for example, we know that the NSA has deals with big backbone network providers to have access to the traffic going by, so they can potentially see everything going by, and they could also potentially inject packets into the network if they wanted to actually launch some kind of an attack. So in general, what these things can do sort of boils down to the same thing, which is they can see traffic going by and they can inject packets into the network. And so those are sort of the major threats that we try to worry about. So the other thing to think about is, well, we have encryption. How does encryption play into this? So when you work, this is sort of the model of how Google works. So what we have is we have on this public internet, we have a set of users that are all connecting from different devices, mobile users, desktop computers. They connect to this Google front-end server. This is the actual web servers that they run. And they're connecting from the public internet. Then once they get inside Google, what typically happens is this front end will decrypt everything, and then all the traffic will sort of go into the Google internal network unencrypted. And it does that because it's a lot faster, it performs a lot better, it uses a lot fewer resources. So even if we encrypt everything in the public internet, everything inside Google's decrypted where potentially it could be seen. So if you can break into Google's network, if you're sophisticated enough, then you can see everything going on in clear text. So just using SSL helps somewhat, but it doesn't actually make sure that things are always protected. So let's now do a quick look at the internet protocol stack. Again, this is going to be a repeat for people who've studied networking. This is not the OSI layer model because we're not interested in models of the internet. We really care about how the actual network works. So there's four real layers that we care about here. One is the application layer. This is the actual application protocols we run. HTTP for web servers, FTP for file transfer, SSH for remote login, IMAP for email or send mail for email. So these are sort of, you know, actually have your data. This is where when you login happens. Below that, we have a transport layer like TCP or UDP. This makes sure that our data arrives in the right order, that it hasn't been corrupted. It can handle taking a stream of data and converting it into individual packets that are sent. Below that, we have the network layer, which is sort of the IP layer. This makes sure that your packets sort of get from one place to another. So this is where routing happens, so that I can send a packet from here. It'll go through a bunch of routers across the internet and end up at Google or Amazon or Microsoft. That's all the IP layer. Below that, we have the link layer, which is really how do you get from where your computer is to the router. So this is things like Ethernet, 802.11, token ring, Bluetooth, things like that. So here we're dealing with something that is very specific to the actual physical network you're connecting to. Everything else is sort of common to all different kinds of networking. So the other thing to think about is sort of what is the networking model? And the model is that the application really just sees things end to end. They assume that they create some messages. Those messages are received in their entirety, hopefully, by another application. There's nothing in the middle. At the transport layer, the assumption is the same, that you generate your transport layer information about the data you're sending. It gets sent to the other side. It doesn't really get modified in the middle. The other side will sort of see exactly the same thing. At the lower levels, though, the model does include the switches and routers. So at the network level, we do have a router in the middle, so we know that we are sending the packet to some router that is then going to look at the packet, decide what to do with it, and send it on. And then at the link level, we have the same thing, what is called a switch, where we send it to a switch, and the switch will then decide where to send the packet on. And so the IP packets could be modified potentially at the switch level, and the Ethernet packets could be modified at the link level. Okay, so when we think about actually sending data, what this means, though, is that if we start at the top with our user data, suppose, for example, we want to upload a JPEG file to Facebook to share with our friends. So that JPEG file is our user data. We then are going to encapsulate it in a protocol like HTTP to actually do the upload with an HTTP post message. So that adds some application layer header information, HTTP colon, the HTTP headers that we saw before. That then gets encapsulated in a TCP segment that adds a TCP header that will say this is the TCP connection, the TCP ports we're talking to on either end. This is a checksum over the TCP data. This is the offset of this TCP data in the stream, so you can tell if packets have been reordered. That is then encapsulated in an IP datagram, which is a packet that has an IP header now that says this is the source address and the destination address we're connecting to. And then finally, when you put it on Ethernet, you're going to add an Ethernet header and an Ethernet trailer that sort of say this is our Ethernet address, this is the Ethernet address we're sending it to. So every layer here adds its own information on top of the packet so that when processing happens at that layer, it sort of knows what to do. Okay, so we're going to start at the bottom now, and we're going to look at Ethernet. So Ethernet was developed at Xerox PARC by this guy named Bob Metcalf in the 70s, and it was actually based on this network that came out of Hawaii called AlohaNet. And the idea was the problem they were trying to solve was, you have a network that connects everybody. How do you decide when you're allowed to send? Everybody might want to send at the same time. There'd be a collision, and so the packet would get corrupted. So the idea that they had here was, well, let's just try to send, but what we'll do is we'll see if something happened. And if something happened, we will then back off and wait a little while and then retry, and hopefully bad things won't happen. So a super simple idea. Like, right, you walk into a grocery store, there's a big line, you sort of stand, you might walk away and come back later to see if the line is gone, and only when there's no line do you actually go in. And the more times you come back, and there's a line, each time you might wait a little bit longer for that congestion to clear. So this is called carrier sense multiple access with collision detection, because we can sort of sense the carrier, so we can hear if somebody else is trying to send. It's multiple access because multiple senders can try to send at the same time, and collision detection means we can tell when we do send if we collide with somebody else. So ultimately, this means that we're going to take turns using the same shared wire in this model. So what are the sort of security problems that could happen here? So one obvious problem is that if we have this sort of multiple access model, then anybody else on the same wire can potentially see the data going by. Because if they can sense the carrier, they can see the traffic as it goes by, so they can very easily snoop on things. So this was a problem when it was actually the case that everybody connected to one wire. At this point, what typically happens, is that the real picture of how this is done today is more the one on the left, where there's a switch and everybody connects separately to the switch. And so you really mostly see only traffic, your traffic to and from the switch, as well as other traffic that is called broadcast traffic, which is data that is intentionally sent to everybody. And so that helps prevent some of these problems. But there's still problems that can arise. So here is sort of the inside of an Ethernet packet. we've got an Ethernet header and a trailer. The Ethernet header has a 6-byte, 48-bit source address and destination address. This is called the MAC address. And when you buy a network card, the network card typically has a MAC address built in. And there's a protocol to make sure that all the MAC addresses in the world are supposed to be unique. So when you want to send something, you have your MAC address, you need to find the destination MAC address, and you put both of these into the packet. You can then say what type of packet it is, because you want to sort of know what is the next higher level protocol, so you know how to decode it. And then there's a trailer, which is a checksum to make sure that the data didn't get corrupted in transmission. So this trailer is one way, the CRC is one way we can detect collisions, because that checksum will fail. So a key question is, how do we know the destination address for Ethernet? And this is generally a problem at different levels. How do we know who we should send a packet to? So one thing that makes it easy is in this switch model, where we have a switch, the destination is pretty obvious, right? Because we always are sending packets to the switch. So this makes it pretty easy for clients at this point to figure out where they should send things. So this is the actual format for the MAC address. So there are some bits in here that will sort of say, there's some classes of address that are sort of multicast addresses, where you're explicitly saying this packet should be sent to everybody by the switch instead of being sent to just one destination. And then you can say, is this sort of a universal, how far should this message go? Is it local or is it universal? And then I said, this comes baked into your card, but you can also change the MAC address. So any thoughts on why you might want to change your MAC address? Has anybody had to do this? So one reason you might want to do this is that, oh, did you have a thought?
Home routers to emulate the computer that's connected to the cable, so that the other side thinks your router is.
Right, exactly. So one way you might want to think about applying security is that in the switch you could say, you can put a policy that says we are on this given wire, we're only going to let packets from a certain MAC address. So our department, the CS department, does this. Every port in the wall, the switch that port is connected to knows that they're exactly which MAC address can send data on that port. This is why in our department, for example, you can't plug your own little network switch in and plug multiple computers into one hole in the wall, because it will only let packets come from one machine. So what that means is that, if your machine crashes and you get a new one and you don't want to bother the lab, you might change your MAC address. So when this one dies, maybe we're going to create a new host, and we're going to sort of keep this MAC address 3 so we can send it. So this often happens where cable companies will want to only let you connect using the MAC address for their router, for their switch. So if you want to connect a computer directly, then you might make it use their MAC address. So the point to know is that MAC addresses are not really secure, because they're not forced to be anything, they're not forced to sort of be a constant value at all times. However, as I said, a lot of people use MAC addresses as a layer of security. So using a layer of security is not a problem, but if MAC addresses is your only thing you're using for security, then you've got a problem. So for example, if our department says, once you can get on our physical network with a MAC address, you can then access our email servers, you can access our file servers, and we don't make you log in, that would be a problem, because they would just be trusting this MAC address that would be changed. So that's sort of one obvious problem you could have here. So this was actually used. Aaron Swartz was a guy at MIT. He decided that he didn't like that technical journals were behind paywalls, and so he wrote a program to sort of download, to sort of download all these open journals and post all these private journals and post them on the public internet for everybody to access for free. He was later arrested and then committed suicide as a result of this, but the way that he got access to the library at MIT without being sort of registered as a student with access was that he did MAC address spoofing, because the library was trusting your MAC address to identify who could read online journals and who could not. And so you could say, you know, this is really the library being lame. Clearly the Department of Justice did not feel that way. So protocol stack. So we're now going to move up. That is sort of a basic problem with Ethernet, is that the addresses can be spoofed. So we'll now look at the next level up, which is IP. So IP has a sort of a richer format with more data. So in here we have a version number. We have something that indicates how long the header is. So we can have variable length headers. We're going to have a type of service, a total length for the packet, an identification for the packet, an IP identifier that we can use, some flags, information about fragmentation, because what if you send a packet and then the next size network takes smaller packets? You might have to take an IP packet, split it into multiple packets. We're going to have a time to live that says, if you're sending this packet, we want to make sure as you're routing this packet, it doesn't go into an infinite loop. So we'll put a time to live that will eventually go to 0 and the packet will be dropped. We're going to have a protocol which will tell us what is the next level up protocol, like TCP or UDP. We then have a header checksum, which will sort of checksum the contents of the header. And then finally, we have source addresses and destination addresses. And then we have some options, which of course are optional to sort of extend the protocol. But you know, the key things are that we still have this sort of, we have addresses that are put in here by the client that identify the server we're talking to. So there's a problem now, which is that my computer sitting here is sending out Ethernet packets, and for Ethernet has to know the actual MAC address to send things. So if I want to send a packet from my computer to Jane's computer right there, how do I figure out what Ethernet address that should go to? So there's a protocol for that. It's called the Address Resolution Protocol. And the basic idea of this protocol is that my computer will send a packet saying, does anybody know the Ethernet level address for Jane's IP address? This assumes that I know Jane's IP address already. This message will sort of go to appropriate sets of computers, and one of them will respond saying, you know, I know that address, Jane's Ethernet address is this 48-digit number. And then I'll say, great, thanks, and I will then start sending packets to that MAC address with Jane's Ethernet address in it, believing that Ethernet will take the packet and deliver it to Jane's computer. So this is a cooperation really between the Ethernet level and the IP level, because the ARP packet has to sort of bridge, the goal of this is to bridge the gap between those two levels, because this is the level where we have different kinds of addressing. So here's what the protocol looks like. You know, like as a standard Ethernet header, we've got the Ethernet header up there, but down below we have the IP level information we're putting in here, which is the sender's IP address, and then there's going to be the response is sort of the target is going to have the IP address for the target and the checksum. So when this packet is sent out, there's a problem that you don't know who it should go to because we're trying to find Jane. So typically you will set the destination address to all Fs. This makes it a broadcast packet. So everybody sees this broadcast packet and can respond to it. And we're relying on the fact that only Jane will say, this is me, and it's my packet. So in this, the ARP, by the way, is an ARP request where you're requesting an address. RARP is a reverse ARP, which is the response, which is the response to the request that actually has the destination MAC address. So needless to say, this is somewhat a slow operation, and so computers will have a cache. Well, they will cache all the addresses they currently know. This is from my laptop, and it says, you know, for this set of IP addresses over here, here are the corresponding MAC addresses. So this is my home network, and there's like my printer and my TV and my kid's computer and her iPhone and things like that. So this shows everything that's been cached. Yes? ARP is Address Resolution Protocol. RARP is reverse address resolution protocol. Or it's the response. So one thing you can do here is you can try, so what you want to do as an attacker to some extent is try to poison this cache. Because you would like me to have the wrong MAC address for an IP address, because that means when you send packets, they will go the wrong place. So one way you used to be able to do this, it turns out that if you just sent out a reverse ARP packet, computers would receive that packet even though they hadn't sent out an initial ARP packet and say, oh great, a reverse ARP packet, I could use that in the future, let me just add it to my cache. And so computers would just sit there listening all day for any ARP packets they got. Whenever they got one, they'd add it to the cache so that if you ever needed that information, you had it already. This is great for an attacker because as an attacker, all you have to do is send a ARP packet for the IP address you want to subvert, send it out there. Whoever has never seen it before will see this new packet and cache it, and then they will now connect to your MAC address instead of the real thing. So if you want to make them connect to you instead of like a department print server so you can see what they're printing, this is a pretty easy way to do it. So this was turned off in like 2005. Most operating systems got wise and stopped letting you do that, realizing that sort of just believing unsolicited data is always a bad idea. So one thing you can do is a denial of service attack. So another thing you can do is you can send, so when somebody does an ARP so every gateway at the IP level will have a gateway address for home net. It often ends in .1, like 192.168.1. So one thing you can do when somebody does an ARP for 192.168.1 is you can send a reverse ARP with an imaginary made-up MAC address. What this means is that computers will try to send all their data to that gateway. So they will now try to send all their data to this non-existent machine, and they will get no network access at all. So this is a way of denying service by connecting the gateway IP address to a non-existent MAC address. So that's one thing you can do. Denial of service is fun, doesn't make you money though. So the other thing you can do that's more fun is you can send your MAC address as the address of the gateway. This means that everybody else on your network will now send all their traffic to you, and you can see those packets and then send them to the real gateway. So you're basically installing yourself as a switch and being a man in the middle. So now every packet going through your network goes through your machine. You can modify it, you can change the packets, you can see what's in the packets, and then send them on their rightful destination. And again, this happens because this ARP level has no authentication whatsoever. There's just packets out there, anybody can send one. So any questions on sort of ARP level attacks and why they happen? Deafening silence. Okay, so another low level protocol. Did you have a question?
The idea there is computers are no longer just for RARPs. You're waiting for one to send a regular ARP request,
right?
Interjecting a bandwidth line. Why would a device send a regular ARP request?
So when a device, there's a couple of reasons. One, when a device turns on the first time, it has to find the gateway, and so it will send an ARP. The other reason is that they're cached with the time to live. When the entries expire, they would send it again. And so as an attacker, you could also, you may not even see the message. If you just are sending RARPs all the time, then when somebody does send an ARP, your packet might get there first because you happen to be sending it at the right time. So it's harder to launch in this case, but it's still possible. Yeah?
So what's a common way to prevent this kind of attack?
So, I mean, a common way, I don't know, to be honest, what the way to protect this attack. So one way is to not accept unsolicited RARP packets. You can also have your switch sort of filter some of these packets. So for example, if you tell your switch, these are the MAC addresses and IP addresses attached to this port, if it sees a RARP packet that doesn't correspond to what it knows, it can filter it out. So, the general approach to lots of network level attacks is to try to detect the attack at a switch in the middle of the network and then drop the packets that are offended. So in this case, if that switch knows the real IP address and MAC address that's connected, that are associated together, it can sort of fail anything else. Okay, so our next link level protocol is 802.11. This is Wi-Fi. It's got a bunch of different pieces to it, basic service, distribution service, extended service. The thing to know is every Wi-Fi network has an SSID, a service set identifier, which is the name of the network. And there's a couple of different modes where it gets used. There's unsecured, which we all know and love because it gives us free Wi-Fi. What's more common is WPA2. This is what most of us use at home, where there's a password. It's called a publicly shared key, PSK. It means that everybody on the network knows the same secret password. It's not a per user password. And then in enterprises, there's 802.1x, which is where you log in with an individual account or a public key or something like that. So everybody gets a different account in 802.1x, which is great for companies, but a pain and sort of a hassle in your home where you're trying to connect your TV and you have to create an account for your TV to do this. So one thing to note is there was an initial effort to secure, so after unsecure Wi-Fi came out, people said, well, let's create a secure version. They called it WEP, Wired Equivalent Privacy. And the idea was we want to make the security of a wireless network equivalent to the security of a wired network where you can control who can plug into it and filter MAC addresses or something. So they created an encryption mechanism, they encrypted things, and it turns out they really just botched the encryption mechanism. So what they said is we're going to use, they said we're going to use the RC4 cipher with an initialization vector, but their initialization vector is only 24 bits. And so the problem is that 24 bits is only 16 million values, and 16 million values means that it's not that hard for an attacker to sort of wait. It means that you're going to use the same initialization vector multiple times. Sending 16 million packets is not that many packets. And if you use the same initialization vector twice, then you can sort of see the differences in what's encrypted, and you can use that to get the key out. And so it turns out that people could break the WEP keys relatively quickly. And so that was sort of a disaster that failed very, very quickly, and that was the origin of this wireless protected access protocol. You notice this is WPA2, and the reason is that WPA1 was, again, a catastrophe that was insecure. So for wireless networking, one of the things that has to happen is your computer has to associate with the network so that it knows when I'm sending packets, where do I send it to? What is the base station I'm using? And the base station will then sort of control how the network is used and how it's shared. So as a network, you're going to send a probe request. The access point will send back a session ID and a MAC address. Your computer will send an authentication request. This is where your password actually gets used that you typed in to verify it. And then the access request, the access point will send back an authentication response to sort of log you in. So can you see anything about this protocol you like? I mean, it's a very simple protocol. Can you see anything here that you like or don't like? That's potentially risky. What are sort of the properties we want in a protocol like this? Maybe it's too general a question. So in general in authentication, there's sort of two directions that we care about. We care as a network, we want to authenticate that the user is allowed to connect to this network. So we would like the network to sort of, we'd like the network to know that you actually have the right password. But the flip side is, as a user, we want to make sure we're connecting to the right network. That if we are connecting to the wrong network, then we should sort of be able to detect that and say, this is not the right network. So we should care that the authentication response here has some way of proving that the access point actually knows the right protocol. So once this all is finished, we then send the associate request saying, okay, we're connected. We now want to actually be associated with this network, and so we're going to be part of the network, and we'll be included in the protocol to share the bandwidth. Okay, there's a response. So one of the problems is that you can actually create two access points for the same network. So if we have two access points with different MAC addresses, when you send this probe request, this is basically a broadcast. Either of these MAC addresses can come back, and as a client, you can't really tell which is the real one. So this means that, for example, I could set up an access point that was named with the SSID UWNet. When you try to connect a UWNet, you might try to connect to my access point sometimes instead of the real UWNet, right? And so you can see how in the simplest case, this is a denial of service because you can't authenticate to UWNet anymore because you're connecting to the wrong server. Another thing you can do is you can sort of set an evil twin here. So we have this MAC address that we're using, and what we can do is we can send the MAC address of some server, some other server on the network, instead of the MAC address for the real base station. This means that your traffic will go to the wrong MAC address to this sort of evil twin. So this means your attacker is pretending to be an access point with the same session ID by sending the wrong MAC address. You're going to try to authenticate to it. You'll authenticate to the wrong one. Now remember, on a public network, everybody knows the password. So if somebody knows the password, they can sort of do this. If the authentication protocol doesn't prove to the client that the network knows the password, then anybody can pretend to be that network and the client won't know the difference. So we can do this two ways. One, we can spoof MAC1. So remember, we can change the MAC address. We can have our server change its MAC address to be the same MAC as the access point to see the traffic. Or we can sort of spoof the probe message to use the wrong MAC address. So another question is, how do you actually get this done? So if somebody's already connected to the right network, how do you get them to connect to yours? If you're just walking into a coffee shop, for example. Well, the thing you can also do is there's a disassociate message that a network can send that says you should disconnect. So as an attacker, you can send a forged disassociate connect message, which will go to the other machines and will tell them to disassociate from the network, which will force them to reconnect. And then when they reconnect, they will try to reconnect potentially to your forged network instead of the real network. And then you get to see all their traffic. So in a way, this is similar to ARP poisoning because we are sort of sending out our MAC address for the session ID instead of the real thing. The same way with ARP poisoning, we were sending out our MAC address, our Ethernet address, instead of the real Ethernet address for a corresponding IP address. And it's for the same reason, which is it's sort of a broadcast network that is not authenticated, so anybody can send any packet they want onto here, and there's no way to prove that you actually have the MAC address that you're using. So one thing that's fun about this is that drones, for example, one way they often work is they'll send up their own Ethernet network. They'll sort of be their own base, or they'll be their own Wi-Fi base station that you then connect to control it. So this means that you can use this attack. It's an unsecured network. It means that you can use this to sort of spoof somebody's network, sort of take control. You can use this to take control of their drone, or you can use it to sort of see what they're doing with the drone because it's an open network and all these vulnerabilities happen. And again, it's because it's only using a MAC address. So you change your MAC address on your phone to be the MAC address of the person communicating with the drone. You can then take over the drone and do whatever you want. So, and it's sort of, the reason this happens is that security and setting up accounts and passwords is hard. So there's a really strong temptation to sort of rely on the existing infrastructure like Wi-Fi or Ethernet to be secure, even though it really lacks the security properties we want. It's just so convenient that everybody thinks, oh, it doesn't matter that much. Okay, so we're cruising up the stack. Hopefully we're not going too fast, but a lot of this is sort of background information. So the next level up the stack, those were sort of, we were just talking about sort of link level and the relationship between link level and the network level. And now we're going to sort of move wholly into the IPv4. So a couple things to note is that there are no notion of a connection at IPv4. We're just sending packets. Every packet is sort of conceptually unique and not related. So we're just blasting out packets. It's up to somebody else if they want to make a connection or make them form some kind of stream. IP packets are unreliable. You send them. The IP layer doesn't really care if they get dropped or mangled. Well, actually, it cares if they get mangled, but it doesn't care if they get dropped. It's up to somebody else to worry about what if they get dropped. It also includes the ICMP protocol, the Internet Control Message Protocol, and this is sort of the, sort of how you sort of control things to get error messages back. For example, if you try to send to an IP address that doesn't exist, you might get an ICMP packet back saying that you can't find that destination address. It's also used, ping as an ICMP packet that just says echo or response back. It's also used by traceroute, a tool to sort of figure out the routes that you're going, all the switches you're going through. So these are the protocols we care about at this level. Again, we have this nice fancy looking packet with lots of cool fields in it. So a question is, what are the things that we care about at this level? What are the security issues? So one thing we care about deeply is routing. Routing says when you put a packet to the network, how does it get to the right destination? So this means that if I can control routing, I can sort of take your packets and send them the wrong place. So for example, there was a time when all the internet packets were like going through a switch, I think in Georgia or North Carolina, because somebody misconfigured routing. Or you could take all the packets destined for Facebook and send them to Russia if you can control routing. So routing is a separate security issue we'll talk about later. But what are other things that we might care about with IP? So one of the problems is that there's no authentication of the source IP address in general. That you can put any address you want in the source field in an IP packet and send it, and nobody really cares. The server, when it will sort of use that source address to send a response, but the source address is actually used for a long time was not enforced by anybody. This, as you talked about defenses against problems, this is the kind of thing that a defense might be. It's to sort of enforce that source packets have the right format. One of the common things that happens at the IP level is a denial of service attack. And the goal of a denial of service attack is really to sort of prevent legitimate users from accessing some service. So in this example, our goal of this attack is to stop legitimate users from accessing the server with the address 1234. So one thing you can do is just send a whole bunch of ICMP ping messages. If you can just get a lot of machines to send a lot of message, or even you as one machine send a lot of messages, every packet you send will make the server do some work and respond to that. And so if you send enough of those, it'll crowd out legitimate traffic. So it's a very simple attack that anybody can launch using this protocol. So a question is, when will this work as a denial of service? What are the situations where just sending a lot of ping messages can be an effective denial of service? Any thoughts? Will it always work? And here we have just a single attacker. Yes?
We have enough equal or greater processing power and bandwidth on the attacker side to have on both sides.
Right, exactly. So we need, because the attacker has to do work here, the attacker has to have more power than the server that it's trying to defend, okay, that it's trying to attack. Similarly, for networking purposes, the attacker has to have more bandwidth, so it can sort of send more packets into the network than the server can receive. So if the server has sort of a limited length, so for example, suppose it is a home server that you're running that has, you didn't pay for fancy service, it's a couple of megabits per second that you're paying for your business. If an attacker is on a fast link, they can just send so many packets, they totally saturate your network link and no traffic gets through. So the key thing to think about here is to find some resource either in the network or on the server itself that you can saturate and consume all of that prevents legitimate traffic. And so it means that in this simple case, the resources are either computing or network, and network is probably an easier thing to saturate. So those are sort of when this will work. If you were trying to do an attack like this from your cell phone, probably you're not going to get very far doing it on your own because you're not going to have great bandwidth compared to a server. You don't have great processing power. How can it be prevented? Well, an easy way to prevent this is to take those switches there that are connected to the internet and do have processing power and do have a high network bandwidth, to have them drop packets. So if they can detect that all these packets are coming from you, then they can say, I see too many ping packets coming from 5.6.7 and 8. I'm just going to filter out all these ping packets. So this is ingress filtering because we are filtering the packets that are coming in, that are coming into the victim. So that's sort of a general mechanism for preventing denial of service. Try to filter the packets out sort of further from the victim, closer to the network where there's sort of more bandwidth available. So how can we avoid ingress filtering? Well, one thing to think about is how does ingress filtering work? So what I said is we have to identify who is sending too many packets, and we have to drop the packets from whoever's sending too many. Because the problem is that there might be legitimate people sending ping messages also, right? I often ping www.google.com to see if my network is working or to see how fast it is. So we want to let those legitimate uses work, but we want to block illegitimate uses. And so we can do that by looking at the addresses that are sending a lot of packets, and we can just filter those packets out. Well, remember I said the IP packet header, the sender address isn't real, isn't checked rather. So what I can do as an attacker is I can just send IP packets with lots of different source addresses. So instead of sending them all coming from 5.6.7 and 8, I can set the source to 8.7.3.4. And so if I use lots of different addresses, that ingress filter won't be able to pick out one address that's generating the problem, because the real problem is coming from a million different addresses. So we're going to overwhelm the switch with sort of too many different sources for it to do effective filtering by faking this source address. So, this you might see happening in your inbox where you might write a block certain senders from sending you spam. And so instead they just sort of subtly vary the email address every time they send a message. Similar when you get a cell phone call from some random number trying to spam you or sell you credit card insurance, they might use a different number every time. So you can't just block that one phone number and block all the traffic. Same exact problem here. So another thing you can do, so one problem with this is that you do have to be able to put in fake packets into the network. And the ISP for the, one thing to think about, who can actually stop you from doing that? Right, so the ISP for the attacker, that switch up there, could do filtering here to make sure that you can't send packets with the wrong source address. So some ISPs will do this. The problem is once you leave that network, it's very hard to do that filtering. So if you can find an ISP that doesn't do source filtering, you can launch this attack. You just have to find one anywhere in the world with enough bandwidth to let you launch the attack. So there's another kind of attack, which is to say, we don't want it to be traced to the actual, necessarily traced to the victim. We want to have somebody else actually send the packet. So we're going to do what's called a reflection attack, where we're going to frame some other server as launching this attack for us. So the goal is going to be to send an attack we're going to send a packet from 5678, the attacker, to 1234, which is the person in the middle, the reflector, cause the reflector to send a packet back to 8734. So the reason this works is most of the time you send a packet to a server, the server sends a response. Right, so if I send a ping message to this server in the middle, it'll send a ping response message. If I use a fake source address, like I use 8734 as the source address, the ping response will go to 8734. So I can then have the attacker bounce messages off of lots of different servers, send lots of pings with the same source address, 8734, to millions of different servers. They will all send the ping response messages back to the same server and overwhelm them. So this is a reflection, because the packets are getting bounced off some other legitimate server in the middle who unknowingly is causing a denial of service. And so again, this is hard to filter out by address because these are legitimate servers you might actually talk to that are generating too much bad traffic here. Is this attack vaguely clear or crystal clear? So the other thing you can do that's even better is exploit asymmetry. So what if we could do something where we send a really small packet that's really cheap to send, and we can do a couple things. We can either cause the victim to consume lots of resources. So if we can send something small and the server will spend 2 milliseconds processing it, that's great. So for example, it used to be in Apache, there was a bug where if you sent a URL that had lots of slashes, then the way Apache would process this would be an O of n squared algorithm. So it sort of like look for this whole string, it would then pull up a slash, and scan the entire string again, pull up a slash, scan the string, pull up a slash. So if you sent a URL with like 1,000 slashes in it, it would go crazy. So we're out of time today, but we will sort of pick up sort of more advanced denial of service attacks on Thursday. And I do hope to have the exams graded by then also. I'm meeting with the TAs to grade them in about 10 minutes.